Hey everyone, this video is about writing transformations from graphs, and this is just the class notes portion. You'll have a separate worksheet for your assignment. Up until this point, we have been given a parent function, and then we are supposed to apply a transformation and then graph the new function based upon the transformations told to us by the equation. But now what we're going to do is look at a graph and observe the transformation that occurs and then write the equation. So we're going to write the equation for g of x, the dashed figure, if g of x is the transformation of the solid figure. So it's really easy for you to get confused on which one was the original one. So g of x is the transformation of f of x, so that means that we're going from f of x to g of x. So f of x was the original one, and then g of x is the new one, and that's the one we're going to write the equation for, write the equation for g of x. But f of x was the solid, so we're going from solid to dashed, and we're writing the equation of the dashed graph, and we're calling that one g of x. So let's start out by looking at number one. If the solid one was the original figure, I can compare the dash and the solid figure, and I can see that they are the same shape and size, so it wasn't stretched or compressed in any way. However, if I just pick a point, it doesn't matter which one. If I'm just going to pick this, looks kind of like a vertex here. I notice it went to the right 2 and then up 1, 2, 3. So actually those are the only transformations that happen. So g of x is the equation we're writing down, but we're going to write it down as a transformation of f of x. So we went to the right 2 and up 3. So we went from f of x, so then we have x. So to designate going to the right 2, we write down minus 2, and then we went up 3 plus 3. So g of x is taking f of x, moving it to the right 2, and then up 3. Let's look at another example. So here we kind of have like this extra kind of W looking thing, and we're going from the solid to the dashed. Okay, so if I compare my x values, I can see that the x values didn't actually change. They're still lined up with where they should be as far as the x values go, but it's the y values that moved. So we didn't move it up, and I can tell that because this y value of 0 remained at 0. However, this y value of 2 is now at 1, 2, 3, 4, 5, 6. So it used to have a y value of 2, now it's at 6. So if I compare this to my other y values, this y value is 1, now it's 3. This one was 2, now it's 6. And again, 0, it's still at 0. That tells us that we are doing a vertical stretch. We're making it taller by a factor of what are we multiplying by to get from 2 to 6, and from 1 to 3 we're multiplying by 3. So this is g of x, and we're taking the y values and multiplying them times 3. And so if we take f of x, multiply their y values by 3, we'll get g of x. Let's look at some more examples here. Okay, on number 3, if I compare the shape, the two of these, the dash and the solid, they are of the same shape. They weren't stretched or compressed in any way. But I can see that where this used to kind of open up, this V here, it now opens down. And also this little vertex, aside from the fact that it was reflected over the x-axis, it has been moved to the left 2. So we can see there was a reflection, and it was moved to the left 2. So g of x is taking our solid figure f of x, and if we are reflecting it over the x-axis, that means that there was a negative in the front, that we multiplied our y values by a negative 1, and then we also moved to the left 2, so we have x plus 2. So it's a good idea to double check. So if we're starting at the dashed figure, if we move to the left 2, 1, 2, and then we reflect it over the x-axis, it gets us to this point. So always double check to make sure that you have it written down in the correct way. Okay, and number 4, again we're going from solid to dashed, so I can see pretty quickly that this is a reflection over the x-axis. They're opening two different ways, but also if I compare my x values, it looks like they got stretched out further from what they used to be. So if my x value was 0, it stayed at 0. If my x value was 1, it's now at, what does that look like? Maybe 1.5. If it was at 3, it's now at about 4.5. And then this one was at 1, 2, 3, 4, 5. It had an x value of 5, and now it's at 7.5. So if we are comparing, probably the easiest one is to look at this x value is 1, this x value is 1.5. Well, if I think of that as a fraction, 1.5, 1.5 written as a fraction is 3/2. And that will help us in just a moment when we write our function. Okay, so we see there's a reflection and my x values are being multiplied by 3/2. Otherwise, though, besides the reflection, the y values are not being stretched. This was at 2, and so this is still 2 from the x-axis. This one was at 2. This one still has a y value of -2, but still the same distance from the x-axis. So my function g of x is f of x reflected over the x-axis, but also the x values are being multiplied by 3/2. So being reflected over the x-axis means there's a negative in the front, and the x values are being multiplied by 3/2. But remember, whenever you write it in your function, you write it as the reciprocal. So we're going to have 2/3 x. So if we double check this, if I take this x value of 1 and I multiply it times 3/2, that'll be at 1.5. And then if I reflect it over the x-axis, that brings us to this point here, and that's correct. Same thing if you did it with -1 times 3/2 is -1.5. Reflect over the x-axis here. So this is the correct answer. Okay, so now for some slightly easier ones. These are clearly absolute value functions because they are the shape of a V. So remember that the parent function sits at 0, 0, 1, 1, 2, 2, and -1, -1, 1, and -2, 2. So the original function looks like this. So we're going to be comparing our parent function to what we have now. So I can clearly see it's reflected over the x-axis, so that means we're going to have a negative sitting in the front. But the x values, if I'm going from this point of 1, 1, its related point is right here. And that x value is twice as far away. So this was at 1, this one is at 2. This one was at 2, and this one is at 4. So my x values are being multiplied by 2. So that means that my function f of x is, so it's being reflected, that means the negative will be in the front, but the x values are being multiplied by 2, so we write the reciprocal whenever we're dealing with the x's, 1/2 x. So it means all of my x values are being multiplied by 2, and we're reflecting it over the x-axis. Let's look at number 6. So here, if I look at the shape of this, it has the same shape as our parent function. It goes up 1 over 1, up 1 over 1. So it hasn't been stretched or compressed. However, it's just been moved to the left and up 3. So my function is f of x equals the absolute value of x. We moved it to the left 2, so that's plus 2, opposite, and then up 1, 2, 3, so then plus 3. Okay, let's check out number 7. Okay, so this isn't quite the same shape as my parent function because it should go up 1 over 1, but here it's gone up 2 instead of just up 1, up 2, then 1. So my y values are twice as high as they used to be. My y values used to be 1 and 2. Now they're at 2 and then 4. And then also I can see that my vertex has been moved to the right 1. So we moved to the right 1 and we've multiplied the y values by 2, which means a vertical stretch by a factor of 2. So we have f of x equals, so we multiplied our y values by 2, that means a 2 will be sitting in the front, but we've also moved it to the right 1, so that's x minus 1. So the right 1, vertical stretch by 2. Okay, on the next problem, it's not the same shape as it was before. I mean, besides the fact that it's opening down, but it should have gone from 0, 0 to 1, 1. But if I'm ignoring the negatives here, I go from 0, 0, and the next x values is 1/2. And then after 1/2, I use 1. So instead of going out by 1, where we had 0, 0, 1, 1, 2, 1, the next one would be 2, 2, I'm sorry, and then 3, 3. So the x values were going up by 1. Now they're only going up by halves. So that means our x values have been multiplied by 1/2. So f of x equals negative because it was reflected over the x-axis, but also my x values were multiplied by 1/2, so I write the reciprocal down of 2. So x's were, we had a horizontal compression by a factor of 1/2, and then a reflection across the y-axis, x-axis. Let's look at number 9. So number 9, comparing this to the original parent function going from 0, 0 to 1, 1, I'm only going up by halves now instead of by 1 at a time for the y values. So that means our y values have been multiplied by 1/2. Our x values weren't multiplied by anything because we're still going out by 1 to get to the next point. It's just the y values are shorter than they used to be. So we have a vertical compression by a factor of, we're multiplying them by 1/2. Then we also moved to the right 3. So this is f of x equals, the y values were multiplied by 1/2, so we have a 1/2 in the front, absolute value of x, and then we went to the right 3, so that's minus 3. Okay, the last two examples I'm going to do with you in class, and those are the check it out 3A, 3B, and 3C on page 160. If you can figure those out, I challenge you to it, but I will look at these 3 problems with you in class and show you how they work. Hope you're having a great day. Bye.